Hello, everyone, and welcome to the Exploring CubeSats module for Full Steam Ahead. I am so excited to be with Paula today, our resident expert in all things satellite. Paula, do you want to quickly introduce yourself for the audience?
Yes, sure. So, hello, everybody. My name is Paula do Vale Pereira. I'm a PhD student in the STAR Lab, Space Telecommunications Astronomy and Radiation Laboratory. I'm doing my PhD in space exploration elements, especially focusing on probes and satellites. I've done my master's in my undergrad back in Brazil, where I'm from, and I did them in mechanical engineering, focusing on thermal sciences. And now I'm doing a lot of mechanical engineering and mechanical design for the satellites in Star Lab. And I really love that.
That is amazing. I'd love to learn a little bit more if that's okay with you. I thought we'd start sort of broad. Can you tell us what exactly is a satellite and what are they used for?
Sure. So the term satellite is really, really broad. There are natural satellites and there are man-made satellites. Natural satellites are like the moon, for example. It's just anything that is orbiting around something. So you have your planet, and then anything that is orbiting around that planet is a satellite. Then if it's not a natural satellite like the moon, it's probably going to be man-made, and sometimes it might be alien made, but let's give that to the future. And the ones that we have that are man-made are what we normally just call satellites. And there are many, many different uses of satellite. Satellites can be demonstration missions, so they can demonstrate that technologies work in space for future use. They can be imaging systems, so either looking down at the Earth to see the Earth from a bird's eye view, or looking to the other direction to see how exoplanets work or how the universe started and how the Big Bang happened, and a lot of things you can see in the satellite. And they can also be doing other type of experiments, like understanding how microgravity works and different technologies. And there is a lot of things that you can do in satellites. And some of the really interesting things is that when you are on orbit, some things are really different than when you are on Earth. And for imaging, for example, that's a big, big thing because, for example, if you see Hubble, like I have a mini Hubble. Everybody knows Hubble, right? Hubble is this great, great imaging satellite that has taken most beautiful images from space and sent us back on Earth. And if Hubble was here on the surface, it would not be able to do those images because the atmosphere that is above us, the atmosphere is great. It protects us from radiation and everything. But when you're trying to take photos, it also blocks or blurs the images that you're trying to see. So if you have something on Earth, you cannot really see those sharp images with all those details. You have to be outside of the atmosphere. So that's a big, big thing for imaging. Being out there in a satellite is what allows you to do amazing sharp photos from out there. And also, when you're trying to image down here, if you are in a satellite, then you have a lot of kilometers that you can be seeing at the same time, and you can get a view from the top. So you can understand maps or continents or geographical locations and a lot of features that you would not be able to see if you were here limited by what your eyesight can give you. There are also a lot of communication satellites. If you are, for example, if you have a cell phone and you want to talk with someone, you need the radio communication to be arriving directly to your cell phone because the radio waves, they need eyesight to transmit any type of information. So whenever you have a tower, the tower needs to have direct eyesight to your phone. But what if there is a mountain in the middle? You have to have first, the earth is curved, so you have to have a lot of towers so they pass through the curvature of the earth, and then also you have to have towers on every side of mountains so signals pass through the mountains. And so imagine how beautiful it would be if instead of coming from towers, it would come from satellites where they can just go straight to you. Like, of course, there are a lot of challenges, engineering challenges with like losses because it's a really long distance when you're coming from space, and pointing to the right person and making sure that the signals don't get crossed and you don't hear someone you don't want to be hearing during your call. But the ability of connecting a lot of people at the same time, and connecting people that, or countries that would not have the ability of having a tower established because that costs a lot of money, that's really big. Like, you can connect a lot of people and connect the unconnected and do a lot of really beautiful things with satellites.
Yeah, so it sounds like satellites are very important both socially, keeping us connected and keeping communication processes ongoing, but also scientifically. It allows us to both look at the Earth and deep into space to sort of answer unsolved questions.
Yes.
Cool. I've been hearing a lot about CubeSats or cube satellites, which is the focus of this particular module. So I was wondering if you could describe the difference between a satellite that we usually hear about and a CubeSat, and why CubeSats might be more advantageous or better to use than a standard satellite.
Sure. So there are many, many different sizes and shapes of satellites. The traditional satellites, as I would call them, are something like the famous Hubble. They are gigantic. Just to give you an idea, this dimension here in Hubble, this diameter is 2.4 meters. Like, Hubble is the size of a bus. It's really, really big. So imagine how much it would cost to make a bus size satellite. It's a lot of money. Like, it can get to the billion dollar scale. And there are not that many players in the world that would be able to spend $1 billion on anything. And so the fact that satellites have become smaller, it's helping a lot to allow more people to use space. And that's where CubeSats come in. This is a tiny model of a CubeSat. It's a Lego model. And this example is what they call a 3 units CubeSat. One unit is a 10 centimeters by 10 centimeters by 10 centimeters box, just like something, a tissue box from Kleenex or something. It's like a unit of a CubeSat. And this cube set comes from this name of being a cube and being able to stack the cubes. And there are some beauties in this CubeSat. First is that they are small, so they are cheaper to produce. Second, they are standardized. So normally you can buy components that are going to fit inside your CubeSat because there are standards and a lot of people follow those same rules. And when you have to do something specifically for your case, that's expensive. But when you buy something that a lot of people are using, that gets really cheaper. So the fact that the thing is standardized makes it a lot cheaper than what it would be if it was not standardized. And then last but not least, even the things that are not standardized, they tend to be COTS, as we call it, which is like off the shelf. And when you're able to buy off the shelf components, install them in a satellite and test them, it's really a lot cheaper. And why are we using off the shelf components? Because now if we have something in a small satellite and it fails, we didn't spend $1 billion. We just spent 500,000 or something, which is a lot more feasible, and you can take a lot bigger risks. So small CubeSats allow you to have bigger risks to try new things. They allow you to have a lot um, less expensive things in space. They allow a lot more players in, and they allow constellations to exist. Because if you need, for example, in the communication example that we talked before, one satellite would not solve the problem. You would need a lot of satellites around the globe to send this data to everybody. And if you had $1 billion satellite, you wouldn't be able to have many of those. But if you have a small, cheaper satellite, then you can't afford having many. So you are able to have constellations and provide a lot more accessibility or a lot more information to a lot more people.
That's truly amazing. Are you finding that more research groups or more educational groups are starting to build their own cube satellites in response to this? Is it sort of allowing space to be a little bit more opened up for researchers?
Mhm. For sure, for sure. There are a lot of universities now that are entering the game doing satellites and they are focusing on CubeSats. And if it wasn't CubeSats, most universities would not be able to spend all the money doing a gigantic satellite. And one thing that I personally think is really beautiful is that this decreased cost on making a CubeSat makes it possible for other countries and other communities to also build their satellites. For example, I come from Brazil, and in my hometown, there is a university that has just like 3, 4 months ago, they have just made their first CubeSat. It's a 1U CubeSat. It's a simple design, but it's a CubeSat, and it's coming from Brazil, from like a small island in the south of Brazil. And that would never be possible if it weren't for CubeSats. It's really a great way of making space able to a lot of people.
It also sounds like it's a great learning tool to sort of apply your engineering skills and expertise to actually put something into space without that risk you were mentioning of sending up something that costs $1 billion and having it fail.
Yes, for sure. You learn so much while doing a satellite, like so much. There is this expression from NASA which just says failure is not an option, and that's like I have some caveats in that expression because sometimes like I think that failing is good because that's how you learn and you have to take risks, and if you're afraid of failing you don't take risks.
Mm.
But what that phrase means is that once you have something in space, you cannot get like a wrench and go there fix it because it came loose. You cannot just quickly go there and tape something back. Like it's there and it's not going to be reached or touched ever again. It has to do its thing by itself. There are really rare exceptions to that case, like Hubble when it was fixed a couple of times. But like most satellites, once they are deployed, that's it. They need to be able to do their thing by their own and not have anything being fixed. So you really need to excel at making sure nothing is going, or the least amount of things are going to fail. And you gave your best to detail and engineer with care every single component.
Paula, you've built a cube satellite before. So I have a couple of questions related to that. I want to know what the process of building a CubeSat is like. You mentioned that process of iteration and daring to take risks. So I'm interested in that component, but I'm also interested in what exactly your cube satellite does. What is the sort of mission that this satellite is accomplishing and what scientific questions is it answering?
Yes. So I really love the CubeSat that we built. So I will be biased to say it's like the great CubeSat. But the process of building a satellite, it has a lot of steps. There is this standard from NASA, and they have a lot of um, tiers, I would say, in the middle. So first, you need to have your mission designed, and you need to find money for your mission. So you have an objective, you have something that you're going to accomplish on orbit, and then you find someone to give you money. So in the case of the CubeSat that we built in Starlab was DARPA. And okay, we got the money. Now we need to do all the requirements. requirements are super, super important in satellite and engineering as a whole, because if you don't know what you need to accomplish, how are you going to do anything? So defining requirements is a big, big step, and you spend a lot of time to make sure that that is really right. And then when you have all your requirements, you go to your preliminary design. And then there is this big thing that a lot of people in space talk about, which is the PDR, which is the preliminary design review. It's a acronym by NASA, and you can search on Google. There's a lot of information about PDRs. And the big thing is that you started your design, you started doing some CAD work, you started getting all your optics specified, you start getting all your components there, but you need someone else to look at it and have a second eye and confirm, yes, I like what you're doing, or being like, hey, have you thought about that? And then
Mm.
what about that other thing? You really need second opinions, and you need people to give you inputs and give you feedback on how you're doing. And then that's the big thing behind the PDR, where sometimes like people from NASA, people from DARPA, people from other labs, other universities come, and then you present for an entire day what you're doing and all the subsystems, as we call, so the structure, the thermal, the communication part, the computer part, you divide it in subsystems, and then you talk about each of those subsystems to those people, and they give you feedback and input. And then after that, you come back, you continue working, and then you go really deep to finish all the detailing and all these specifications in each of the components. And then you have the other big thing, which is the CDR, which is the critical design review. And that's what people know as before cutting metal. So after you have your CDR, you get the same people again. Everybody discusses all the subsystems in your satellite again, and everybody goes through, okay, structure. Everybody approves, everybody approves. Thermal, everybody thinks it's okay, good. Communications and propulsion and everything. And most of the times you end up with action items like give more specification to this item or change the position of that item or something like that. But then after the design, the critical design review is done, is when you are okay. Now I can start sending things to machine shops. I can start cutting things out. I can start spending my big money on this, and then you start really assembling your satellite. And the assembly process is also really intense because you have to do everything in clean rooms. You cannot do it everywhere, because if you have any type of dirt in your satellite, when it goes to the vacuum of space, it can damage optics, it can damage electronic components. So it's really, really bad if you have dirt on your satellite. So you have to assemble everything in clean rooms, and you have special components to put in your satellite, because even if they are off the shelf, they are like special off the shelf because they are radiation tolerant or radiation hardened. Because here on Earth, the atmosphere is great. It helps us a lot. It protects a lot of radiation. But when you are above the atmosphere, there is a lot of harmful radiation being shot at you all the time. And one big thing that radiation does is that it flips the bits in the electronic components. So as soon as you have a bit flip, then your entire code, like it
Mm.
can be a tiny thing that makes not much of a difference, but if it's in a critical bit, then you can like completely go around and mess your code. So there are a lot of things that we do to work around radiation. We normally have two, three things doing the same thing, like because so we have a component and then a second component to make sure that we have redundancy, and if one fails, the other one is still working. We have watchdogs, so they keep like comparing the results, and when we see the results don't match anymore, then for example you turn off your satellite and you turn back on again. If it was a small bit flip, that fixes it. If it was a big amount of radiation and it burned something, then it turning off and on again doesn't fix it. Sometimes you can still have your satellite working. Sometimes that tells you your satellite ended. But So there are all these radiation things that you have to keep in mind, and you have to buy special components for that. And then that's the assembly process. But after you finish assembling, you also have to test. And testing is a big chunk of time, and it's a big commitment. There are two big main tests that we have to do in CubeSats. One of them is thermal vacuum test, and the other one is vibration test. And why do we do those? We do thermal vacuum test because in space, it's vacuum and it's cold. And when you are in the nothingness of space, the average temperature is like 3.8 Kelvin. Here in the moment, we are at around 290 Kelvin. So that's how far it is, to give you an idea. I don't even know how that would be in Fahrenheit, but it's probably really cold. And then, so it's really, really cold when you are in the emptiness of space. But then when you are orbiting the Earth, when you go in front of the Earth, between the Earth and the sun, then you have all the sunlight hitting you. And like, you can be super cold, but then having a lot of sun, and sun heats you up. So we're like super cold, super hot, super cold, super hot. Will that break anything?
Mm,
You have to first do some simulations and some calculations, and then test to make sure that nothing is going to break or nothing is going to deform or big things like that. And one important thing is that being in vacuum, you cannot use fans or any type of blowing convection air thing. You have to rely purely on conduction and radiation. And conduction and radiation might not give you all the heat exchange that you need. So you really need to design thoughtfully. And then the second test, which is the vibration test, is really stressful because when you put your satellite in a rocket and it goes to space, like Saturn V, this guy shakes a lot.
mm,
Like there is a lot of vibration. Like if you look for videos from astronauts, you will see they go like and if you have something that is a little loose in your satellite and you start shaking it, it will come loose. And like that cannot happen because you cannot go there and fix it. So you have to make sure that everything in your satellite is designed to stay well tight and not come loose and not break during vibration. And then you have to test it. So you get your satellite, the baby that you spent a lot of months building and years projecting, and then you put it in a table and the table shakes it. And you are like, no, it's my baby. So it's a stressful test. And when you pass vibration test, you're almost done to put in a rocket and go to space. And what about the CubeSat that I built? So I was part of a team in Star Lab. It was an amazing team. Like I love those people. And we built the Deme, the deformable mirror demonstration mission. And this is the patch. And the thing that Deme was trying to do is that it receives light from exoplanets and tries, or from exostars, and try to identify exoplanets. Why is it hard? There are a lot of different ways that you can try to identify exoplanets, but all of them have their flaws and their gaps and their difficulties. And the one that we were trying to do is direct imaging. So you look at the star, you see the light from the star, you see the light from the planet. But the light from the star is really a lot stronger than the light from the planet. So for you to be able to see the planet, you have to block the light of the star. Okay, good. This is called coronagraph. But when you block the light of the star, there is a lot of diffraction that passes on the edges. And then when you get the light from the planet, it's so full of errors and noises from this diffraction that you cannot even tell the planet. So what we are doing is that we have this thing called a deformable mirror that in here is being represented by this yellow shape. And it's Simply a mirror that has, it's a micro electromechanical device, or MEMS, if you want to search for that in Google. And it has a lot of tiny rods under this mirror. And then we can turn on, for example, this rod, and then it boops the mirror up and deforms the shape of the mirror. So when we receive the light on the mirror, the light is full of noise, which means that the wave front, or the front of the light, is not flat, is all noisy. Then we measure how noisy it is. We deform the mirror to that same condition. And then the light that is reflected from the mirror is now flat because it was corrected by the deformation of the mirror. And then when we have this corrected flat wavefront, then you can see with a lot better contrast and you can identify the exoplanets. And we have that mirror in the CubeSat. We built it, we tested it, we launched it. It's currently the International Space Station. It's just waiting for the scheduled date when the astronauts are going to get it, put it in the deployer, and send it to orbit. So we are really looking forward to that day, which sadly is not yet scheduled. But as soon as Deme is on orbit, it will start receiving light from different exoplanets. And we also have a laser inside in case we can point to an exoplanet. We can use our own laser to do that type of correction and make sure that it works. And then the big goal is demonstrate that this technology works, because being a small CubeSat, the amount of light that you receive is really, really tiny. So we are not going to be able to see something that Hubble has not yet seen or something like that. So we are going to see things that we already know exist, and we are going to confirm or compare them to make sure we have a better contrast. And we will then demonstrate that having a deformable mirror on orbit works. And that's the beauty, because we can use a CubeSat that is relatively cheap and quick to build and prove something that gigantic satellites like W1st could use in the future. So it's really, really nice, and I love Demi.
It sounds super cool, and it sounds like a really great way to demonstrate the technology that you guys are exploring.
Yes.
One thing that stuck out to me is the level of collaboration that's required for a CubeSat, and how many different minds and different subsystems it takes to address all of these, not only environmental factors that you have to design for, but
Mhm.
also the sort of process of going through that, those design reviews and sort of jumping over those hurdles. What is the timeline for your CubeSat build, and how many people were involved?
Our CubeSat timeline was around 3 years. That's for CubeSats, that's normal timeline. If you go to big satellites, then it goes a lot longer. It can be like 20 years or something. If you Google James Webb Space Telescope, you see how long of a time it can take to make a satellite. But a CubeSat is like 2 to 3 years. That's a decent timeline for a CubeSat. And in MIT, we were 9 people, and this each one of us has a different expertise, and we have to collaborate and keep exchanging information to make sure that we build the entire thing right. So the subsystems that are the most in, like, there are 10-ish subsystems, and all of them need to communicate with each other because you need to keep exchanging information. So for example, if I'm doing the mechanical design, I need to know how large the antenna is going to be, or how heavy the mirror is going to be, or where the electronics need to be, because I need to design to that. But then the people in the computer also need to know how much data the communication antenna is going to be receiving and sending, so they can match the amount of bits and bytes. So everyone needs to be communicating all the time. And the from those 10 subsystems, I think that the ones that are universal, so every satellite has, because some they don't have. First one is mechanical, so all structure and how everything's going to fit and where everything's going to go. Thermal, so making sure that you don't burn anything and you don't freeze anything when you are on orbit. C and D age, the name that we call it, which is command and data handling, which is basically the computer and how all the data is going to be flowing in the CubeSat. Then we have communications, how that data is going to be sent back to Earth, and you're going to be able to receive it and do something with it. Then there is payload, which is what the goal of your satellite indeed is. So what you really are trying to accomplish is the payload. And then attitude control, you need to make sure you know where you are and you can control where you're pointing to. And then there are other ones that can be there, like propulsion. You might need a propulsion in your system, or imaging. You might need optics depending on what you're doing. And then things can get really specific. But every satellite needs a structure, every satellite needs data to be handled, needs communication systems. Oh, I forgot a really important one, power. Of course, your satellite needs
Super important.
power. um, you need to receive power from the sun, most likely, and you need to store that energy somehow and keep using it when you are behind the Earth and not receiving the sunlight. So most CubeSats have solar panels, like this here is representing a solar panel. Most CubeSats have solar panels, and then the solar panels receive the sunlight and turn that into electricity that can then be stored in the battery and used to give life to all components. And it's a really important system. There are a couple of systems that we say that if they die, the satellite dies. And if power dies, satellite dies. If communication dies, satellite dies because you cannot get anything from it. So it's just a brick in space.
We don't want that to happen.
Not at all.
So Paula, I want to thank you so much for sitting down with me virtually to discuss your work. I have one last question for you,
Yes.
which is um, for young people watching and wanting to learn more about CubeSats, how do we become the next Paula? How do we get to build a satellite within our lifetime?
I'd say that going forward, the number of opportunities are going to open, like many opportunities are going to be there. So, first one step is keep your eyes open and your ears open and make sure that you read about the subject and you know what is happening. And one big thing is be ready when the opportunity comes. You don't know if you're going to be able to start building a satellite next year or if you're going to be able to start in 10 years. But study the subject, like read about it, learn about it, and when the time comes that you need to do it, you are ready. You hit the ground running. You have everything that you need in your mind. So really study a lot, learn as much as you can about the subject, and know what is happening, see all the opportunities that are available around you, and give the best, to give your best as well as you can do, is really try to put your heart into it. And this sounds cheesy, but if you really want it, you will get it at someday because you will put your soul into it. And besides that, I'd say that a big thing that is important is that somebody needs to trust you. So, for example, if my advisor hadn't accepted me into MIT, I would not be here building a satellite. So, somebody that has power, let's say, needs to bring you in and say, like, I put my trust on you. And that's also hard to accomplish. And I'd say that the best way you can accomplish that things, like there are two big things. First is make sure that your work speaks by itself. So get good grades, write research if you can, like, I don't know, mathematical Olympics, physical Olympics, like really build up your CV and make sure that when someone looks at your profile or at your resume, they're like, okay, this person really knows what you're doing. So really make the work speak by itself. And second, build relationships. But be honest when you are building these relationships. Like you should, the big goal should be build a relationship because you want to talk with people and you want people to be happy and you really want to connect and have friends, and being kind and connecting to people is going to open a lot of doors for you, and it's going to give you a lot of good people talking good things about you is going to open a lot of doors. So be kind, maintain nice relationships, and work really hard so your work speaks by itself. Yeah.
I think that's great advice. And I think one other takeaway that I learned from you, Paula, is that it takes all sorts of different minds to create a CubeSat. There's electrical people, and there's physics people, and there's hardware people. And so I think as long as you follow what you're interested in, there are many different ways to get involved with the build of a CubeSat, like
Sure.
including policymakers and sort of social
Yeah.
scientists that help to make important decisions regarding funding and implementation of different infrastructures that allow for these cube satellites to be built in the first place. So many different ways to get involved.
Yes, for sure. There is a
Awesome.
spot for everybody.
Great. Well, I'm excited to maybe one day build a cube satellite myself. Um, Paula, thank you so much for your time today. I encourage all of you to seek out more resources related to the things that Paula was talking about, some of which can be found in this module. Um, Otherwise, happy exploring and super excited to have you contribute to Full Steam Ahead. Thank you.